Hello, I hope you find yourself well. So today we're going to continue um, tentatively finalizing, or if not, I'll just add another topic in next lecture on time-independent perturbation theory, where we have already seen how to calculate the transition probabilities, and we have seen also Fermi-Golden rule. And towards the end of this topic of time-dependent perturbation theory, we'll try to understand how the electromagnetic fields can affect atoms such as hydrogen atoms or hydrogenic atoms. So let me share my screen and let's start the topic. Okay. Yeah, so this is a particular topic we're going to focus on. I'm not sure if I will cover today selection rules, which is an extra topic that I want to mention even briefly, because I think it's important in the context of this topic. But anyways, so again, we're gonna think on how hydrogen atoms interact with electromagnetic fields, and we're gonna perform an approximation in physics that is known as the electric dipole approximation. So this is useful because this type of interaction is important for understanding how lasers affect atoms, and also to discover a process that can basically explain the finite lifetime of excited quantum levels, which is something that you would not expect essentially from uh, quantum mechanics when your knowledge is only based on the stationary states, right? Because, well, you find the different energy levels and then you would assume, okay, there are stationary solutions. So they should stay there in time. We will present arguments into why that doesn't happen. But in any case, so there are a couple um, simplifications that we'll perform. The first one is that, well, so the atom is going to behave like a dipole, so that's fine. The simplification comes first into the fact that although we are dealing with an electromagnetic radiation, the magnetic part can be disregarded because its effect is um, lower, smaller. So we can focus mostly on the electric part, even though we have a time-dependent field. And the second is that, well, formulas might be similar to what we saw before in the Stark effect, where the electric field was constant, with the difference that, first of all, now it's time-dependent. But the second approximation, or the second simplification, which is called the electric dipole approximation, is that for the range of visible light, um, the wavelength is way bigger than the size of the atom. And because of that, we will approximate the electric field as being or having no spatial variation. So that is the main meat of this electric dipole approximation. And again, it's a comparison between the affecting light and our subject of interest, which is the atom, right? So we're going to neglect the spatial variation of the electric field. And in that context, we're basically going to have a formula that looks similar to what we saw in the Stark effect, with the difference that the electric field is time dependent, making therefore the perturbation Hamiltonian also time dependent. And well, we know that electromagnetic fields can basically be added linearly. So it suffices up to some point to do the analysis for a single frequency and then use linearity, essentially. So let's assume that we have an electric field of a single frequency omega. And in that case, okay, we know it's time dependent, so it's oscillating at this frequency omega. Then it is assumed to be uh, constant with respect to the position variable, and that's why we have this the magnitude. And this factor of 2 is only to make things simpler when we express the cosine in terms of complex exponentials, right? So this looks nicer. And there is a vector of direction, epsilon, which later on is going to be related to polarization considerations, but I'm going to omit that for the moment. So again, this looks very similar to also the harmonic perturbation problem that we saw last section. So in that context, basically the perturbation was a constant term and then cosine of omega t. If I plug in the formula for the electric field, given that I have this electric dipole Hamiltonian, then I'll substitute some terms come out, then I'll have basically the inner product of the dipole with the polarization vector. And just to basically match these two expressions, this would lead me to conclude, having done this algebra, that essentially the B in here would have to be this. So, well, B is like this if I want to basically match these two expressions. And the last piece um, in the puzzle is that the electric dipole moment, as we know, is basically the charge, which is minus E times R. And if we substitute for D in this formula, we simply have that B is, um, well, a positive electron or positive charge of the same magnitude as the electron, magnitude of electric field, and then polarization direction, uh, inner product with R. So the case of a single frequency had been studied before in this simple setting. And we know that the transition rate will be proportional to a Dirac delta. So again, this is the rate of change of the probability transition coefficient. And the proportionality factor is this, where we have the matrix element norm squared. And yeah, by definition, BFI is basically the matrix element of this operator B, right? Which is what we obtain in here. So I can pull out some terms out since they're constant, particularly the vector of direction of the electric field. And then I have this inner product with this element, which might be also interesting. And if I plug in these formulas in the rate of change, this is the proportionality factor for the Dirac delta. So again, at this point, we have assumed that we have a single frequency, uh, making a jump to a single final state. But there might be two differences with respect to these assumptions. One of them was studied before, which is what if the final state is not a single, discretely defined state, but some sort of continuum around an expected state, but there is some spread of energies around it, and we can transition around that basically to any element of energies in that interval. So that we saw before. I'm going to make use of that later. But first, well, so far we have assumed that we have a single frequency. I talked about linearity, etc. And in reality, we might not have a single frequency, but we might have many, right? And not only many frequencies contributing, but basically all of them incoherent and with light that might be unpolarized. So most importantly about the incoherence, because we will have to add in our study basically over the respective transition rates, assuming the incoherency. So that's important. So simply we will perform this study first. For the other, we will catch up based on information that we have seen in a previous lecture. And actually, I mean, if you think about this thought experiment, this is basically, or the first one, is the situation of a black body radiation interacting with atoms. So simply you have many possible allowed frequencies which are incoherent and are going over a gas of atoms. And you know, before quantum mechanics had an equation such as Schrödinger equation, um, Einstein performed a semi-classical statistical analysis of this problem. There was an element that he used of quantum mechanics, though, and that is basically Planck's black body radiation law. So that's important, but of course, that was a preliminary stage of quantum mechanics in very early stages. And so up to some point, the following study that we'll present has a lot of elements of basically classical statistical physics. And I'll make the comments on when we're using these classical approximations and where we are using, say, Planck's black body formula. So again, we'll go over this analysis of Einstein of black body radiation interacting with atoms. And the assumptions in this setting is that we have a black box that contains both a gas made of atoms. The assumption is that they can live only in two discrete energy levels. And then we have also black body radiation inside, which are just, you know, incoherent electromagnetic waves just dancing or moving around this black box. So the radiation and the atoms are assumed to be in thermal equilibrium at temperature T. You may have just let the system go on over a long time. And well, for a single frequency, so before we go into the jump of many frequencies, if we consider basically the volumetric energy density of an electromagnetic field of a given angular frequency, omega, fixed at this point, so we know how the energy is in an electromagnetic field, right? It's basically half of it is due to the electrical component, half of it is due to the magnetic component. You can therefore basically use twice this value for the volumetric energy density. And if you were to plug in the situation that we have is that, well, the electromagnetic field is oscillating, therefore its amplitude and its magnitude too. And plugging in the formula for E, well, we'll have the magnitude, and then we have the oscillating component, both of them squared. So, well, I'm going to make a jump from one single frequency to many frequencies, but I have to be careful with the argument. The following is just a mathematical statement, meaning that, okay, we know our trig identities, meaning that basically if I integrate this over the time period of a given frequency omega, so I'm still at a single frequency, well, this integral is going to be the time period. On this other, we have these two. If you think of symmetry considerations, this is basically twice this integral. So I have this, and therefore this just gives me a formula of the integral of cosine squared over its time period, given that I have a frequency omega. So this is t over 2. So why is this math important? Because still in the analysis of a single frequency, if I basically make the time average over a period, which is why we have the RMS index over here, of this formula. So I know it changes in time, but I mean, although it's oscillating, it's probably proper to study for this frequency what happens over one period. And that's the reason we're performing the average over the period. So it's the integral over the period divided by the time period. So we perform this integral, which, okay, is proportional to the cosine squared over the time period that we considered before, divided by t. So this will capture a factor of 1/2, and that's why we have the two epsilon naught, the permittivity times E naught squared. So that's the result of basically the average over a time period of this energy density, although it's oscillating. So the important thing, if you look at the formula, is that this result is independent of the frequency omega. So, I mean, of course, each frequency omega has its own time period t, which are inverse, etc. But this result is independent of the frequency. So this is a process that we will do. We know that we have basically a packet where there are some, or there is some range of frequencies which is mostly important. And if we consider basically a time period long enough such that all these frequencies are well regarded, then we can basically consider the result for the whole electromagnetic field containing incoherent radiations of different frequencies. So basically, the assumption is identify the non-negligible frequencies, choose a time period long enough so that you do not miss um, any sort of power when you do the integration over time, and then you're good, and this result will still be valid. So under this assumption, where basically you have to choose t properly long enough, then this will be still holding, and you can consider that the result for the whole incoherent sum of radiations, provided you choose an adequate time period. On the other hand, I might make a change of variables. Well, it's not quite a change of variables, actually. What happens is that now I'm allowing this formula to depend on the frequency, because I have many possible frequencies. So um, allowing this as being a sum or contribution of different frequencies, I can express this as a density of frequencies, and then, this is a differential element, right? So this is the result of integrating or, adding differential contributions of frequencies in a given range. Then I have this density function, and this will give me this result. So this is the result having basically added all incoherent frequencies. And this is the proper density that I need to perform the calculation. So that's why rho of omega is called the electromagnetic field volumetric density per unit angular frequency. So basically the other one was a volumetric density before, and this one is also including basically density per unit angular frequency, because now we have allowed the frequencies to be in a range. So again, uh, this URMS is a differential contribution in the span of frequencies considering this differential element. So, okay, so far so good. We have this formula which extends for uh, the sum of incoherent radiations. Um, we're gonna do a substitution over here, basically, which is this is equal to this, which is equal to this. So therefore we have these two. And passing to the other side, we have a formula for the magnitude of the electric field um, at a given frequency, given the uh, basically angular frequency density. And of course, I have a differential element, right? Because at the end of the day, I'm adding contributions. So yeah, I mean, so far I have given consideration of how I can add the contributions of different frequencies. And so we have this so-called broadband radiation. And we will use this result in the previous formula. So if you go to up to this point, we had used a single frequency. Now we need to consider that we are adding contributions of different frequencies. So we could add them, or basically taking an integral, which is what properly we need to do. So if we go to this formula, we have the sum over frequencies of this formula. I mean, this is very hand wavy. The proper way to do this is to actually take, excuse me, an integral over all possible frequencies, where, we had the term E0 squared, which is preserved when we have the sum of different frequencies, and we know that it's related to the density um, per unit angular frequency. So when we perform the integration, we had to include this density in the integration process. Everything else is constant for the purpose of integration with respect to angular frequency omega, except the density and the Dirac delta. And well, we're integrating over domain 0 infinity. So this is going to localize this function over this argument, as usually the Dirac delta does. And that's why this amounts to an evaluation of the density at the frequency omega f5, which is related to this transition between final and initial states. So, okay, using delta properties, we're up to this formula in the case where we have multiple incoherent frequencies. And the second thing that I mentioned a little bit before, um, verbally, but not in the text, is that the radiation is not only incoherent but also unpolarized. So we have a polarization vector which can take different directions. I mean, we have this black box with many radiation incoming and ongoing. So I mean, you have many things going on, right? And the direction is not fixed; it can change, or you have different elements and different contributions. So you also have to consider those possible cases, and you have to integrate over all possible directions for the spatial average, because that's what we'll use later on. And intuitively, you basically live in a 3D space, so you can expect that you'll have a factor of 1/3 just due to that. Actually, if you do the calculation, that's what happens when you perform this spatial average. So let's show the result. Well, this is a notation for average where by taking a spatial average. This is different from the brackets that you have in quantum mechanics. This is just saying that you're going to take a spatial average of this quantity, where basically you allow this quantity to change in a solid angle. So, the angular coordinates can change, and that's why you're taking an average over precisely the solid angle. And so that's why you divide over the integral of the solid angle, where you can have variations in azimuthal and polar angle. So you have this, then you have the integral again in the angular coordinates of the proper solid angle with its Jacobian. So the polar angle can go from 0 to pi, the azimuthal can go from 0 to 2 pi. I can do the same expression for the solid angle in this part. So I just have to integrate this with the proper Jacobian. Um, if I basically separate by Fubini's theorem these integrals, well, the polar integral will be from 0 to pi of sine of theta d theta. The azimuthal one is an integral from 0 to 2 pi of the phi. And so, well, that result would be basically, on one hand, this one is 2 pi, and this would be a factor of 2, so that's why you would have 4 pi over here. And you can also do separations in this part. First of all, you have to understand that, I mean, so um, you have basically these vectors. Some of them are normalized, etc. I think we're also taking R to be normalized at this point. Um, yeah. So, well, basically, what will happen is that you'll have the cosine of theta. I might make a slight change in here, which might not affect actually the rest of the lecture, but maybe I just want to add perhaps instead of an arrow, a hat. Um, well, so let me write this. And yeah, well, the reason is that, I'm performing that integral. Probably in the notation, it was assumed that the norm of this vector was 1, but I just want to make it clear. Uh, so this one is normalized, the other is normalized. When I take inner product, their norms are 1, so that's why I only stand for the cosine. And I have cosine squared times sine of theta d theta. So again, I can do separation of variables. I perform the azimuthal integral separately. I perform the polar one, which is having this Jacobian and then integral of cosine squared of theta from 0 to pi. Some things will vanish, especially the factor of 2 pi over here. So you have a factor of 2 in this part, resulting from this other. And well, if you do this at this point, this is manageable because this is basically cosine cube of theta divided by 3 from 0 to pi. And so you'll have 2/3 divided by 2. This is 1/3. So this is just trying to account for the fact that, the radiation can have many different directions. And so regardless of the vector R defining the dipole, um, you'll still have different frequencies around it of different direction, regardless of the orientation of R. And so you have to consider in account. And pretty much at this point, you can basically disregard this term as accounting for a factor of 1/3, just because you have different directions. So this is a coarse approximation, but it's valid in the sense of the fact that we're using incoherent radiation of different frequencies and different polarizations at this point. So yeah, so see why I jump from this formula to this formula, where the difference is that I don't have the polarization vector anymore. I just have the substitute of a factor of 1/3, which was not appearing here. So that's basically the jump from this part to this part based on this formula. And yeah, I mean, I can keep the R. I don't need to normalize. I only need to normalize it here, so this is fine. Um, so yeah, again, in here, the vector is of norm 1, so we're good. Okay, so far the result is that the transition rate in the limit, of course, as time going to infinity, is proportional to this density in terms of the unit angular frequency evaluated at the frequency of transition, the Bohr frequency. And on the other hand, so we're going to start to comment on Einstein's analysis, because he did it before quantum mechanics knew what was the Schrödinger equation. There was already some early stages of quantum mechanics in terms of black body radiation. But in his study, he had already performed semi-classical statistical analysis. Um, so let me add something. So he already knew or thought in his analysis that the transition rate would be proportional to the volumetric energy density per unit angular frequency. So basically what he's thinking is like, well, um, the more intensity of the energy field you have at that frequency, the more probable the transition will be. And so it will be proportional to it. And there will be a coefficient of proportionality, which he actually called the B coefficient. Now we know it in the community as the Einstein B coefficient. So this will be his notation, the letter capital B, for absorption and stimulated emission, which are processes that we have talked about before. And what we have namely obtained before is a formula for this proportionality coefficient. So this was an intuitive argument, and actually the study of Einstein goes further. But up to this point, the cool part is that via quantum mechanics, which of course we know in a later stage, and he was not lucky enough to know it, we know the formula for this coefficient. And so given these two formulas are the same, of course, in this limit in our case, BIF in the limit had to be or has to be equal to this. So first of all, the important thing is to notice that, okay, this is basically a transition from state I to state F, but at the same time, in the matrix element, you have to take norm and their square. So remembering that, I mean, R is a Hermitian operator, it's due to an observable. Therefore, you know, the relation between exchanging these is to have a conjugate, complex conjugate appearing here. So the transition rate from I to F is the same to I, just because we're taking norm squared, you know. So that's the first consequence, which is nice from the formula that we have. The second is that we know that the frequency of transition is related to the difference in energies, right? So this was the Bohr frequency that we studied before. I'm sorry, there is some noise going on. I hope it doesn't affect the lecture. Um, oh, great. Okay. Hopefully it will go away a little. Okay. So this is giving you a formula for the Bohr frequency in terms of the energy differences. And well, I mean, in this notation, basically you have the negative frequency for the opposite transition. Um, so what we're going to assume is that the intensity of the electric field for this frequency will be the same for its negative. So this implies, I have to say this as a mathematician, I mean, because I have done my study of the topic in different references, and this is an assumption needed in order to obtain what follows. So assuming this, which implies that basically the density of, so these are physically reasonable assumption in terms of, you know, um, the available frequencies in the black body radiation. And that will imply that essentially you'll have the density at this frequency equal to its negative. And of course, I mean, I'm being careful enough since both of these are basically non-negative quantities, so I'm just taking appropriately the range of frequencies, right, to not have a negative sign in there. So under these assumptions, which imply this one, then the transition rate will be such that the transition from I to F is the same as F to I. Because on one hand, we knew that the B coefficients are the same, regardless if we go from one or the other. Uh, so in here, we need this assumption in order to conclude this, which I try to justify in terms of these physical grounds. So the conclusion from this is that the rate of stimulated emission is equal to the absorption rate in this case. Um, so again, we have an external electromagnetic field, which on one hand is stimulating the emission of basically a quantum of radiation by lowering the state from say 2 to 1, right? Which was a higher energy and it goes to a lower energy. Or the absorption where it takes part of the available radiation and it jumps to a higher state. So up to this point, it would seem that, you know, because the rates of going from one state to the other, since are the only two possible levels, and the transition rates are the same, then it would seem that actually the populations of the initial and the final states would be the same up to this point. However, that is not what we observe in experiments because it's known that the occupation of states decreases with the energy. So basically, the population of states obeys a Maxwell-Boltzmann distribution in the semi-classical stage. I mean, so how can the populations be equal? That is not what we observe experimentally. And so the contribution or the idea of Einstein was that there should be another process, which is a third process different from stimulated emission and absorption, which we're going to call spontaneous emission. That basically, out of nowhere, suddenly, well, seemingly out of nowhere, the atom is going to decay to the lower energy state, emitting a quantum of energy in the process spontaneously. So this process is going to make us or make the population densities obey the Boltzmann distribution, assuming we are in thermal equilibrium, which is necessary. So again, I mean, the reason it's called spontaneous is because this occurs without an external electric field. There is a story into why this is happening, and the fact, I mean, the short story, which I will emphasize later, is that this external field is actually the background or the ground electromagnetic radiation, right? So if you have read something about quantum mechanics in popular science, you might know that, you know, I mean, the same way we have a ground state in the harmonic oscillator, light also has its own ground state, and so you're never out of radiation in a way. You're in the lowest state, which still has some energy, and so this sort of background radiation that is basically stimulating the spontaneous emission. But I mean, I'm just saying that basically there is no external electric field that we are applying ourselves. It's just in the environment. But I have to explain more into that. Okay. So this is the cool conclusion. Basically, confronted with experiments, we have to concede to the existence of another process, which is again this is spontaneous emission, but also that excited states, although they're stationary states, um, and they're allowed by the quantum mechanics, you know, with eigenvalues, etc., stationary uh, Schrodinger equation by so-called time-independent Schrodinger equation, which amounts to evaluation of eigenvalues and eigenvectors. So those excited states, they have a finite lifetime because essentially by spontaneous emission, they give a quantum of energy to the environment and then they decay to a lower energy. So in this case, where we have two only possible states, we go to the ground or the lowest energy state available in assumed by the model. So that is very cool and very interesting, especially because we did not expect this finite lifetime for the fact that the eigenstates are stationary, you know. So this is baffling. I think this is quite interesting. Of course, this indicates importance to confront things with experiments, but also there is a new notation for this process for spontaneous emission. So Einstein distinguished it from the others by using the letter A. And so, of course, there's an Einstein coefficient, which he defined as A to I. So I and 2 are basically the two possible states in our black body or black box. And well, the notation is indicating that basically you go from the higher energy 2 to the lower energy 1. So this is the order that is involved in the notation. And again, the higher energy state goes to the lower state 1, decaying spontaneously and emitting quantum of energy. So think of this A to 1 as A2 going to 1, right, with the arrow. But you write it like this. Yeah, again, so the reason, or this kind of like side note comment of why there is no such thing as a spontaneous absorption has to be explained later on, but I need more information and I will just basically comment on it as a conclusion. So the following part is also semi-classical in the sense of the study of population densities in the two different states. And so the notation is that N1 is going to be the number of atoms in the lower state 1 of lower energy. You want, you can call this a population. And then N2 is the number of atoms in the higher energy level 2. So it's a population in the state 2. And we can propose a model for how, you know, the populations change in time, so the rate of change of populations. And the model would be probabilistic on the understanding of the different processes that we have, which are basically, you know, spontaneous emission, then the absorption, etc. So I want to emphasize that the model is probabilistic in nature in the sense that, I mean, it's not quite first principles in a way, but it's quite reasonable in the sense that uh, it follows some sort of exponential growth law. So let me comment on the model to give you more info into why this happens. So I'm commenting on the rate of change of this population of atoms in the state 1 with respect to time, where I can gain atoms or lose atoms. Now, how can I gain atoms in the population of the state 1, right? So basically, for example, by spontaneous emission, I can be in the higher state 2. So basically, this depends on how many atoms I have in the state 2. And then by spontaneous emission, decay from the state 2 to the state 1, right? And I would gain elements in the population 1. So that's one possibility. The other is via stimulated emission, which essentially, okay, I have atoms in the higher state 2. Then I have radiation, external, coming from the black body, etc. And the fact that it has some external radiation stimulates the process of decaying from 2 to 1. So the difference between these two is that this one is stimulated, meaning that it happens in the presence of the electromagnetic field considered, and this other is spontaneous. Again, ultimately, this is due to the ground electromagnetic energy, but first of all, that was not understood at the time. And second, I mean, it's not external, so that's why we distinguish between these two. Anyways, both of them are proportional to how many atoms you have in the state 2, so that's why the model is probabilistic. And then how can you lose atoms in the population 1, right? So basically that would be the absorption, where you absorb energy from the external electromagnetic fields. And given that, you jump to the higher state and therefore you lose an element in this population 1. And so That's why it's proportional to how many elements you have in one. And you have this gain minus loss um, to keep track of how many elements you have. The analysis for this one is exactly equal. Not only equal, but actually, I mean, we have, we're assuming conservation of mass in a way. Because in this equation, now how the population 2 changes in time, it's basically going to be the negative of this one. So that when you basically add these two terms, you have that the rate of change of the total population is 0. So you have a conservation of mass equation, which gives you this, the right-hand side of this one is the negative of this other one, which kind of makes sense because the only possible ways you can go is from 1 to 2. So what one gains, the other loses, since we are having a conservation of mass thing. There is a name for this type of models. So first of all, they are probabilistic. I haven't given a first principle justification. It's just basically based on like, well, how many atoms I have, and therefore the rate of change is going to be proportional to this. I mean, that is um, that is screaming of exponential models, right? But the names for these types of equations are master equations, just so that you know. It's quite reasonable, though. I mean, it makes a lot of sense to propose this model. And well, second of all, is that we already have some knowledge into this transition rate, right? So we knew that the transition rate is proportional to the well, the density of the angular frequency via or proportional included with the Einstein B coefficient. So in the notation, we have that R going from 1 to 2 is B1 to rho of W21. Remember the assumption that we did in terms of rho of W21 equal to rho of omega 1, 2, sorry, omega. And therefore, well, we can have the same notation, but this part will be equal to these two. If we substitute, so far I haven't made the assumption that B12 is equal to B21, you know. That can be concluded actually from the following study, although we already know it because we have the actual formula for B12, you know. So what we're doing is following a little bit into Einstein's analysis before the knowledge of the formula that we got in the first place. So plugging in these formulas in the respective elements for R12 and R21, we have these equations. So again, well, basically, one is the negative of the other. And let's consider the steady state when t goes to infinity, where essentially this term will be 0, right? Because now we don't have any change. We have achieved some sort of equilibrium state where the size of the population does not change. So the rates are 0. The right-hand sides are basically a negative of each other, so we can stick to analyzing one of them. And in the case where this one is 0, basically, for example, we will have this formula, right? So I pass to the other side, basically, for example, N21, and I have N1, B12, rho uh, of omega to 1 minus N2, B21, rho of omega to 1. So I'm using also this in this part. So I have plugged in. So why am I doing this? Well, because essentially I'm going to think by analogy and find that the equation that I get is very similar to Planck's blackbody radiation. But you have to give me time in order to conclude this. So I have this equation which follows from the assumption of equilibrium that at t goes to infinity, this derivative is 0. Then if I basically divide by B12 and N2, I'll have this term on this side and then this. So on one hand, here I have the ratio between populations. Here I have the ratio between coefficients. Here I have the density in terms of angular frequencies. So this is a volumetric energy density in terms of angular frequencies. And it is due to the ratio between the A and B coefficients. Uh, we'll show, first of all, that the coefficients are equal and etc. But the point is, okay, I can polish my expression, pass things to the other side. And this is the other piece of information that was important for Einstein's analysis, which is that he knew the formula that Planck got for the black body energy density. So Planck, in the early stages of quantum mechanics, knew that the energy density as a function of the angular frequency obeyed this formula. And so this looks pretty similar to this one in the sense that, okay, he has a constant term, then he has the inverse of difference, where this difference, well, actually, one of the terms of the difference is this exponential of h bar omega divided by kBt and then minus 1. So at this point, it wouldn't be enough to conclude that we have the same thing. But if we remember, okay, we're in the equilibrium case with a given temperature T, etc. So we know from equilibrium statistical mechanics that the populations obey a Maxwell-Boltzmann distribution depending on the energy, meaning that the population according to the energy is basically my Boltzmann factor exponential of minus c divided by kBt, where is the energy in this case, and then just normalized. So I don't care too much about this constant because if I take the ratio between N1 and E2, the constant is the same, so it goes out. I have the ratio of its exponential. So I have the exponential of the difference between E2 and E1. And if you basically use your formula for the Bohr frequency, this is h bar omega 2 1 divided by kBt. So this is actually quite encouraging because this term on the assumption, well, which comes from experiments, so it's not an assumption, it's using the information from experiments, that this ratio will be exponential of h bar omega 2 1 divided by kBt. So now the equation actually looks quite similar. And so we are led to conclude that evaluating this at omega 2 1 will basically get formulas for this ratio and for this ratio. So that's the next part. And this is the cool part of the analysis, right? That we are using basically the formula for black body radiation proposed by Planck to explain the differences that they were having essentially with the previous classical statistical physics. On the other hand, the Maxwell-Boltzmann distribution, that is also an experimental piece of information. And then basically making these two expressions equal at the frequency omega 2 1, the Bohr frequency for the transitions. So this part or this side is the same as this one. In this other, you have this on the knowledge that, this ratio is actually this term, which coincides with this term. So, I mean, at this point, since these two are equal, I only need to do two matchings. And in a way, it's by analogy, but it's well informed by the data available at that time, which is, first of all, that this ratio has to be equal to this. Okay, so that's pretty cool because I have a ratio between the A coefficient and the Einstein B coefficient. And on the other hand, I can also conclude, I mean, given that precisely this was equal to this, that the ratio between B21 and B12 is 1 coming from this part. So meaning that the B coefficients are equal. And so that's also pretty nice. Um, So that's why we can refer to a single Einstein B coefficient in this situation, and therefore the ratio between the coefficient A21 and the B coefficient. So that's pretty cool. I mean, pretty cool analogy or thinking by analogy. So basically, we have rederived in a semi-classical way what we knew about Einstein B coefficient, meaning that B21 is equal to B12, of course, under the assumption that omega 21 is equal to omega rho of omega, well, rho of omega 21 is equal to rho of omega 12 in the process. So that's important. I have to mention that. And again, the proportionality relation between the Einstein coefficients, the A coefficient and the B coefficient, has this factor. Um, the most important part is that we have found before the formula for Einstein's B coefficient via quantum mechanics. And remember that it was proportional to the square of the matrix element, norm squared actually. So that's why B12 was equal to B21. So we knew it beforehand, but we have concluded in a semi-classical way of thinking. And then using this knowledge, I can plug in the formula for B12 over here, and I'll just have this. So, well, that's pretty nice. Um, excuse me. So the conclusion of our study, we'll make still some further comments, is that excited states decay due to spontaneous emission. And so they have a finite lifetime. So that's something that you could have not known only from a stationary Schrodinger equation, meaning the time independent knowledge of the eigenvalues and eigenvectors. But confronted with the experimental data, you have to lead to that conclusion. And most importantly, we can estimate the finite lifetime of these states by a simplified master equation, where let's assume, okay, there is no external stimulating electric field, and only spontaneous emission plays a role, right? I mean, so there is no external field in this case. And in that case, you have this equation, like in the absence of all the stimulating processes, like stimulating emission or absorption, we only have spontaneous emission. That's why we have the single term. And this is an equation that you know how to solve from your ODs course. I mean, this is an exponential equation, and actually exponential decay for the matter. So if you were to integrate, basically pass this to the other side, dividing, then you have the derivative of natural log, then you integrate and you have the exponential decay model that you would assume. So this is telling you how the excited state decays in an exponential fashion with a finite lifetime. Again, at the end of the day, this model is probabilistic because it's saying that the rate of change is proportional to the number of uh, elements that you have into your higher state 2 population. And well, if you define basically tau as the inverse of A21, you can see that you'll have that lifetime tau, right? So again, lifetime is a concept related to exponential terms. And yeah, um, so the final lifetime in the exponential decay model for excited states is the inverse of this, which we had obtained before. And so we have the formula now by just taking inverse. So there is some other comment that I want to make, which, well, yeah, I mean, think that excited states will eventually decay in the absence of, this stimulating electric field. And so they might survive only for a while, right? Um, so you can only observe the state while it's not negligible. And so that puts a limit on the observation time that you have available to measure or observe that state or its energy. So that is also gonna give you a limitation in terms of the uncertainty of the energy of the associated state. So basically, we go to our Heisenberg uncertainty relations, where we have that the uncertainty in the energy times uncertainty in time is of the order of h bar squared, and thinking that basically the uncertainty in time, meaning the time the state survives, is at least proportional to tau, the lifetime. So again, these are basically order of magnitude considerations, so that's why we have the squiggle. So around or equal. That means that the uncertainty in the energy is inversely proportional to the lifetime, meaning that if the lifetime is very small, the uncertainty is very big, basically because the excited state survives in such a small time that it's very hard to measure. And most importantly, we know that the tau lifetime is inverse to the transition rate. So we have this, right? I mean, the faster we have this transition rate for the spontaneous emission, meaning the faster it decays, well, the harder it will be to observe it experimentally, and therefore the uncertainty in the energy will be bigger. That's pretty much it. Now, the final two pieces in the explanation is like, well, where is the spontaneous emission coming from? And so there is no external electric field um, applied by us, but in quantum mechanics, if you go to the study of basically quantum electrodynamics, etc., you know that there is always some sort of background radiation, which has to do with the fact that you understand light as a harmonic oscillator, and therefore there is a lowest um, energy state, just as in the ground harmonic oscillator, which still has some residual energy of h bar omega over 2, just as in the harmonic oscillator. So you're understanding light or electromagnetic radiation as harmonic oscillators, and there is always a ground energy. So what is happening in spontaneous emission is that the quotation marks stimulating electric field is basically the background radiation of this ground state of the lowest energy level. So that's the explanation. If you are a purist, you would say that formally speaking, then there is no such, well, there is no, can I say? Um, there is no spontaneous emission in the sense that it's actually occurring not out of nowhere, but due to an electric field, even if it's, the background radiation or the ground state in the lowest energy. But okay, we're basically making the distinction between when you have an applied external field applied by you, by the experimenter, a physical situation, etc., or just in the absence of that process, right? And then, okay, there's always like some energy in the background in the environment around us in the form of a residual ground state electromagnetic field. So there is one last comment into this process is like, well, why is there no spontaneous absorption? And I mean, that would lead to energy violations essentially, because, okay, let's think about this in more detail, right? So let's say that we had absorption, which would be so-called spontaneous, meaning that it would be stimulated from the background uh, electromagnetic field or background light, which has a ground energy and it's in the lowest state. Well, basically you would need to absorb radiation in order to jump to the higher level, but then you would have to absorb it from the lowest ground state of light. But then where can it go on one hand if it's already in the lowest state? And how can it give you its energy if it's in the lowest energy state possible already? So that cannot happen. So basically, spontaneous absorption cannot exist because it leads to issues with basically energy conservation issues, or even like the ranking of energies, as opposed to spontaneous emission, which can exist without these issues. That's pretty much the short answer. So try to think about it a little bit. um, so I'm trying to present where this spontaneous emission process is coming from. Okay, so one last comment. Yeah, it's related to the other possible situation that we commented at the beginning, which is laser excitation, in the sense that you might have a single frequency, as in laser, but the final state is not a single one, but it's basically an span of energies around a main state, right? And so let me take a cup of water. Mm. So the other possible situation, we commented on it a little bit before, is where you have a single frequency as in a laser, which, okay, has a single frequency. By the way, I mean, just as a comment, I don't know if you have seen this in your previous courses or not, but laser is an acronym for light amplification by stimulated emission of radiation. And so going back to what we're saying, okay, we have a single frequency in the laser, and so it interacts with an atom, and then it makes it transition to a continuum of higher energies. Now, why would this happen in the sorts of processes that we're studying, right? So this is just a formula that we knew before when we had, the basically Fermi-Golden's rule, et cetera, et cetera. So why would that happen? Okay, so basically the continuum of energies that we would have, you would have available, even if in a small interval of, size 2 epsilon. Uh, so that could be due to a spontaneous emission. So basically you have a localized higher energy state, and then it decays because it's a higher state and it spreads out, meaning that it goes to basically lower energies in the process quickly when you decay exponentially, right? So, um, well, this is the sort of justification that we're going to do. And again, I mean, there's an uncertainty in energy and time when they multiply each other, they're of the order of h bar. And in this case, the uncertainty is of the order of the lifetime. So you will have an associated uncertainty in the energy, and that's part of where this interval of size epsilon is coming, right? So it's related to this uncertainty in energy. So before we had obtained this transition rate in the limit as time goes to infinity as proportional to this density of states per unit energy evaluated at the final state. But we have to know it from somewhere, right? So, and we know that the energy is proportional to h bar omega. So it's also density in terms of frequencies, even if hidden, as, you know, chain rule by concatenation of variables. So, well, the way we can obtain this density per unit energy is via Fourier transform of the electromagnetic field that we have available. So I'm not going to do that. In fact, I'm going to leave it to you as a homework problem. But you can calculate that the Fourier transform of in the case of a spontaneous exponential decay of a higher state is a Lorentzian distribution. So basically, you can conclude that this density of states per unit energy is equal to this. So you have the Lorentzian distribution in this case. I'm going to use also some notation that I have for the processes. This is a homework problem. It's doable. I mean, I'll give you elements to solve it when I post the homework. And well, its integral from 0 to infinity is 1 because the number of states over the possible energies is just 1. And it's just a single state related to the high energy decay. So we have a span because the state, of higher energy is decaying. You have a finite lifetime that affects also the uncertainty in the energy. But at the end of the day, it's a single state. Okay. So, well, we were provided by a formula that you will prove in your homework. We will use this formula by plugging it in the transition rate that we had for these sorts of situations where we have a span of continuous final states. We're simply going to do a change of variables to go instead of the energies with the frequencies. And so, I mean, basically this is, yeah. I mean, this is just a change of variables in the sense of how to change densities from energy to frequencies, And I mean, this is basically saying, okay, the density times the differential element in frequencies is the same as the density of energies times the differential element in energy, so that basically the number of states that you get by calculating over the respective differential elements is the same. I mean, this is actually quite easy because let's say that you go to calculate f or this density as a function of the angular frequency. Well, what you would have is, if you want to think about it as passing to the other side, is basically the Jacobian of the energy with respect to omega times the density of energies. But I mean, this is not only a linear relation, but also proportional because the energy is proportional to h bar omega. So this just amounts like this, just amounts for a factor of h bar, which is what we multiply our GE, and that's why we have h bar squared. And if we simplify by basically dividing in both numerator and denominator by h bar squared, we get this formula. So now using this formula and then plugging it back in, knowing that we have basically R proportional to G of E, where G of E is basically F divided by H bar, which will pick up factor of H bar in the denominator, and that's why we have it dividing by H bar squared in here. So this is just substitution. We plug in the formula that we had for for F of omega, having eliminated the H bar squareds in here. And well, also we're gonna plug in the matrix coefficient element before. So at this point we have this, where we have the polarization vector, the electric dipole operator R, which is important. And it's also important to notice that, okay, the formula for Einstein's B coefficient was this, and we did this spatial average approximation to disregard the polarizations in the case where we have different frequencies. And so we can basically um, add the factor of 1/3 in here. So we would basically plug it in. Well, in this case, you have a single frequency, so that's fine. So, okay, we're just simply doing a substitution in order to get a simplified factor in this way. I'm just collecting terms in order to basically introduce Einstein's B coefficient in this case. I will, yeah. So at this point, let's see. So using just this piece of information, basically going to this part, I have, yeah. So I'm gonna use these parts, use this relation to put Einstein's B coefficient, then I'll have a factor of 2. There will still be like some epsilon naught constant coming from this part that I have to multiply in order to satisfy equalities. I still have the magnitude of electric field squared, but this is proportional to the density as a function of the angular frequency. And so with the knowledge that the intensity of a single frequency laser is equal to 2 times the speed of light times epsilon naught times magnitude of electric field squared, I can use this formula and basically plug it in here, um, to write this transition rate as proportional to the intensity of a single frequency laser divided by the speed of light, then times the Einstein's B coefficient, and then the frequency. And there is one last piece of the analysis, which is what I was jumping ahead a little bit, which is this form, right? So we have this density as a function of the frequency, which, you know, essentially, I want to make like some analysis of it by simply dividing and multiplying by 4 pi. Actually, what probably will happen is that I normalize this. So I want to make it a function easy to analyze. And by basically factorizing appropriately via this term, which then is recombined with all this other part to become this, so that I get 1 in here, then including factors in the square, I'll simply have the difference between the frequencies to the Bohr transition frequency divided by A21 over 2. And so this is constant, and this is a function of omega, the frequency, right? So the point is, where does this function have its maximum? And so, and also, where does it get half the maximum? So I'm going to show a quick picture to basically make you see the intuition in terms of the analysis. And so this is this same function that I had presented, right? So of course, the maximum is going to be when omega to 1 or omega is equal to omega to 1, because I mean, this is inverse to this object, of course, when it is smallest, then you have the greatest value. So meaning that when omega is equal to omega to 1, then this denominator will be the smallest, and then this would be the biggest, and the maximum is centered there. So far, so good. The second part is, where do I achieve basically half this height, right? And so that is studied in order to define some sort of width to this function, because Lorentzian distributions are harder to study. You know, I mean, it's not as a Gaussian. I mean, the Gaussian decays very quickly. Lorentzian actually, I mean, it has a tail that if you define how it decays via integration is harder to manage. So we're just trying to defining amplitudes, well, half width in terms of the interval in which you achieve half the height of this function. So basically, we get that the value of the function at a frequency is half its maximum, where basically this would be equal to 1, so that we have 1 over 1 plus 1 equal to 1 half. And so that's why, well, in understanding that that would be equal to 1, and then passing to the other side, well, it is when this difference, especially because I'm taking squares, would be equal to plus minus a to 1 over 2. So basically, so that is a plus minus because you can be at that height either on this side or on this side. And if you then consider the total width, which is going from here to here, that means that you have twice this. Well, so that means that you have a to 1 as the width of this interval. So again, this is related to a concept that is called full width at half maximum. So again, full width at half the maximum. And therefore, by the analysis that I have presented you, the length of this interval, it's basically a to 1. So just the difference between these two. If you want to know more about laser excitation, you can find the remaining on the info on McIntyre. For the moment, I have presented what I consider is enough for this analysis in terms of our purposes. And the last part that I'm gonna finalize, actually, yeah, I think I'm gonna make the comment because it's not about finishing the lecture, it's more about rounding the knowledge now that I have presented the final pieces in the puzzle. And so I want to talk briefly on something called selection rules and forbidden transitions. So I'm just gonna mention the basics that you should know. If you want to know more in detail part of this information, I encourage you to read either McIntyre's section 14.4 or the appropriate Griffiths sections. But I'm going to try to give a brief account of what's going on. So what we have seen so far from our previous study is that the transition rate between two different atomic levels, it is basically proportional to this averaged element, right? Which is, well, I mean, in the average that we did via this justification is equal to the norm squared of the matrix element of epsilon, polarization vector inner product with R. And so this is the transition rate that we obtained. Of course, this was basically performed by taking a spatial average where regardless of the direction of R, since we have many radiations, this is basically, you know, can be averaged over the whole solid angle, and this gives a factor of 1/3, disregarding the polarization vector and just focusing on this part. So that's why we use this coefficient. Now, what this is telling you, okay, we have proportional to the density, excuse me, energy density, or frequency, or density in terms of the frequencies. But it's also proportional to the square, a norm squared of matrix element of FRI. So one simple conclusion based on the assumptions we have made in the analysis is that when this matrix element vanishes, the transition rate is 0, at least in the electric dipole approximation. So again, up to the approximations that we have made. So that's why there is a name for cases in which this matrix element, basically the matrix element of the operator R with indexes F and I, F being the final state and I being the initial state. For example, the name for the case where this matrix element is 0 is called forbidden transition, because it cannot happen. Because if this is 0, then the transition rate in this limit under the approximations, of course, will be 0, and then it doesn't happen. Now, the opposite, essentially the set of conditions to be satisfied in order to have this matrix element non-zero so that this transition rate does not vanish is called selection rule. There is one very simple, which is also very general selection rule, and that has to do with basically the operator R itself and the parity operator or parity considerations. Because look, this is a vector operator, of course, Hermitian, etc. And I mean, it has odd symmetry with respect to the parity operator. meaning, well, basically it has hot symmetry. So where is this going to come up? Where you perform an integral over space given an initial state and a final state, you know? So in order to get a non-zero matrix element for an odd symmetry operator, basically the related states need to be opposite parity. For example, I even and F odd. And why? Because think about it, just do the mental calculation, do it in your mind. You're going to perform an integral where you have states I and F or given parities or symmetries, sorry. And then you have the operator R multiplying. So you're going to perform an integral over R. Now, R is an odd function, right? I mean, think about it for a second. On the other hand, then you have the products of F and I. And so you need these two being of different symmetries, either one odd, the other even, etc., so that when they multiply this odd function, the whole integral is even, and in principle, it wouldn't vanish by parity or symmetry considerations. Because the worst case would be, let's say, when F and I have the same symmetry, meaning both of them odd or both of them even, because their product, Fi, when performing the integral, will be an even function if both of them have the same parity. And then that product is then multiplied with R somehow, which is odd. And then you have an integration of an odd times an even function. So the function to be integrated at the very end will be odd, and therefore the integral will be zero. So in the case where F and I have the same parity, this mental calculation has showed you that essentially, first of all, the matrix element will be zero. Second of all, because of this, the transition rate will be zero. And so in the electric dipole approximation, notice the emphasis that I'm making to it, when the states F and I have the same parity and the operator is the vector operator R, the transition is going to be forbidden because the matrix element is zero. Okay? So that's very general. In fact, we could do the calculation in our minds, of course, under the assumptions of the electric dipole approximation. The second, this one is the one that I just want to comment briefly. If again you want to see the details of the calculation, please read McIntyre. There's only so much that I can cover. And so now what we'll consider is the conservation of angular momentum when you make a transition across different states. And so that's the second set of selection rules. So let's consider that you have a photon in these transitions. And in the electric dipole approximation, this photon, so we know that the photon has angular momentum, basically spin, which is integer because it's a boson, and second, it's a magnitude 1. And so then if you go into the considerations of angular momentum coupling for hydrogen-like atoms, uh, the selection rules in the electric dipole approximation such that you conserve orbital angular momentum and exponential along components is such that, well, basically what is happening. So you have electric fields, right? So that's why the photon is coming into the consideration. It interacts, then it changes the orbital angular momentum, right? And therefore, in this approximation up to what we have assumed at this point, the change in the orbital angular momentum between the initial and final states for the hydrogen atom has to be of plus minus 1. And then the change in the quantum number m, it can be 0 or plus minus 1. So I have to also mention that these selection rules that I have mentioned over here have already the parity considerations that I mentioned before already incorporated. So essentially, this is important because for hydrogen atoms, there are no electric dipole transitions between states with the same orbital angular momentum, meaning where delta L is equal to 0, that is not allowed. That's a forbidden transition because delta L has to be equal to plus minus 1. So, well, this is also important because the quantum number determines the parity. The short answer of why this happens is because some transitions can be understood simply by analyzing the integral of spherical harmonics. And so when you do the separation of variables, if you simply look at the spherical harmonics integrated and their indexes then you see when some integrals vanish and which other ones don't. That's the short answer. If you want to go over the details, please read Griffiths. And well, you probably have seen this before in your previous quantum mechanics course, where there is a spectroscopic notation to be used, which is letter-based for the quantum number L, meaning that, well, the case L equal to 0 has the letter S, the case L equal to 1 has the letter P, the case L equal to 2 has the letter D, the case L equal to 3 has the letter F, and then you continue alphabetically. We're here, except for these two. So basically, the allowed transitions such that delta L is equal to plus minus 1 in this spectroscopic notation are that, well, you can stay in the same state, right? So let's say that you are in the state S, which is the lowest L. Well, you have to go to P. Then P can go to plus minus 1, meaning higher or upper in L, so it can go to S or D. Then D can go to P to F, etc., so that you have to satisfy this. But you cannot stay in the same L in the interaction with the photons, essentially. So I have hammered the phrase in the electric dipole approximation. And so why is that? Well, the reason I have stressed it is because we have made these approximations basically of a given order with respect to define structure constant alpha, although I haven't explicitly mentioned it at that point. And so far, think about what I have done. First of all, in the electromagnetic radiation, I disregarded the magnetic field because it was basically a higher order in the approximation with respect to the fine structure constant alpha. So that hasn't been regarded. Then I also made the electric dipole approximation of not considering special variations of the electric field, etc. So the point is that there can be higher order terms which can actually allow the transitions that have been forbidden so far under the assumptions of the electric dipole approximation, which has let us obtain this formula, right? So the types of transitions beyond the electric dipole that you might consider later on is basically of the nearest order with respect to alpha, the fine structure constant. Some of their names are electric quadrupole or magnetic dipole. Basically, this one, for example, is because I have disregarded the magnetic component of the electric field. Quadrupole, I mean, basically, if you remember, you have dipole, quadrupole approximations where you have these multiple functions. Maybe you have not seen this before. This is more like either mathematical methods or physics or second course in electromagnetics. Well, doesn't matter. The important part is that these are higher order terms and they have their own set of selection rules, meaning that they will have their own derivation of their transition rates and perhaps with a different operator. And therefore, you know, the transitions might be allowed in that case, although they're forbidden up to the limit of the electric dipole. And this is not in the scope of the course, definitely. So I'm just mentioning that I mean, do not think this is the absolute word, as in any mathematical model. We are subject to our assumptions and they are good up to a point. And yeah, I mean, you can even have higher order approximations, higher than the other two mentioned, which are octupolar, magnetic quadrupolar, higher multiples. This has to do with something called a multiple expansion, which actually, if you analyze dipole in electromagnetics, you might remember what I'm referring to. So it has to do with how far you see away, say, your atom, and then you have expansions of the electric field, which is of the order, well, the potential is of the order 1/r, and you proceed with the expansion, etc. So, but that's beyond the scope of the course. It's not a course in electromagnetics. So again, the point is that a transition may be forbidden in the electric dipole approximation, but at the next order, it may be allowed in a higher order multiple interactions. But I mean, this is enough. Even at the end of the day, although basically the second part of this paragraph has been more focused on atomic transitions, you have to understand that a selection rule is basically given the transition rate obtained, which is proportional, for example, in this case, to the matrix element, norm matrix element squared, actually, that's their proportionality. You have to think that the transition is forbidden if this matrix element is 0. So that's a notation of when a transition is forbidden. and then the condition so that it doesn't vanish in principle, it's called a selection loop. So that way of thinking is more general, and I mean, of course, it's way most important in the hydrogen atom or hydrogenic atoms, but I mean, it can be used for other purposes, at least the understanding of this existence of notation of forbidden transitions and selection rules. So this would be the end, actually, of time-dependent perturbation theory. I really wanted to present this part, even if briefly, because it ties well with the other knowledge. So I think it's quite useful that you see the last part all entangled within itself. So this would be the last lecture before the spring break. I wish the exam is going well, or the first midterm. When we come back, we'll complete the last piece in the puzzle regarding quantum dynamics, which is basically Schrodinger equation as a time evolution problem. And that is related to the adiabatic approximation and Berry's phase. But, well, for the purpose of time-dependent perturbation theory, this section is finished, this lecture as well, although there is one last thing in the model, which is not completely independent, which is why I have put them together in the module, and we'll put a homework that is related to all time-dependent perturbation theory and adiabatic approximation. But you'll see that lecture and then the homework until you come back on spring break. So again, best of luck in the midterm, and have a good spring.